seem to be the only person talking about the bomb calorimeter, so here we go. So our introduction, our bomb calorimeter is designed to measure the heat liberated by a combustion process. And so our objectives for the lab are to familiarize us with the physical properties, the method, and the analysis techniques, determine the thermal capacitance of the calorimeter itself, and then determine the gross heat of combustion of the provided samples. So the theory behind it is the heat of combustion is the number of heat units released by a unit mass of a substance in a combustion reaction in a constant volume apparatus. Heat is transferred to the surrounding water environment by conduction, and you observe the temperature rise in surrounding water, and allows you to calculate the number of heat units released. Basis for the experiment is the first law of thermodynamics. Q is equal to mCv delta T, or mCv is equal to Q over delta T, where Q is the heat of combustion, mCv is the thermal capacitance, and delta T is the temperature rise. For liquids and solids, we assume that Cp and Cv are equal to each other. Then we choose the calorimeter as the system, excluding the fuel, and we know what the fuel is that we're burning. We say that mCv of the calorimeter is equal to Q over delta T, because we can find the Q value from our tables and an equation. When the unknown fuel is burned, you have to do it the other way, where you are finding the heat of combustion, which is mCv of the calorimeter and times the delta T. In both cases, you need to account for the energy added to the system by the ignition wire. If you don't, your data is going to be off. So our apparatus is the PAR oxygen bomb calorimeter. You see on the top right, number 2 is the stainless steel bomb itself. This is where the combustion will take place. Number 5 is the water bucket. That's the water bath where we'll be measuring the temperature as it changes. We have a thermocouple and we have a stirrer. And then the bomb itself, the bomb lid, which is number 1, has all the letters on it. It contains valves, electrodes, and the ignition wire, as well as the fuel crucible, where you put the sample in there to have the ignition wire ignited. Then you have the bomb housing and the lock ring to make sure it doesn't explode. So the bomb prep, you gotta cut 10 centimeters of the nichrome ignition wire. No more than 1.1 grams of fuel into the crucible. This prevents damage to the bomb apparatus itself. Then you add 1 milliliter of distilled water into the housing. Carefully put the lid on the bomb, hand tight, and remove the air. You remove the air by pressurizing the bomb to 30 atmospheres using an oxygen bottle, and you just purge it over and over again until you assume that you have a perfect oxygen environment inside of the bomb, keeping it at 30 atmospheres when you're done. Then the bucket, you gotta put 2 kilograms of water into the bucket and position it into the calorimeter jacket itself. There's a fill line, you gotta reach it. It should be plus or minus 5 degrees Fahrenheit of room temperature, the water. And then there's a grounding button in the center of the calorimeter jacket that it needs to touch. You start the computer and open the file, and you plug in the thermocouple, and then you check that it's responding by just squeezing it with your hand. It should come up to temperature really soon, as we've seen in previous experiments. The time constant is pretty small. So, then you place the thermocouple into the bracket and the calorimeter lid, and you're ready to acquisition software. And then you carefully place the bomb into the water bucket. Make sure not to disturb the fuel, and then you check for bubbles, which would indicate your bomb is leaking water inside of it, and that will ruin your experiment. Then you connect the electrical lead to the terminal. Check the continuity of the circuit. It should be should read 0 ohms when it's a perfectly continuous circuit. Otherwise, there's a break somewhere in your wire, and you have to check that, because you won't get ignition properly. Then you install the calorimeter lid, and put the drive belt on the stirrer rod, and off you go. And then, so for the procedure, you log the room temperature for 2 minutes or so. After logging, you press the button to ignite the fuel. You continue logging data until an equilibrium is reached. You stop logging after the equilibrium, but don't take so long to stop logging that the water starts to cool down after the process has happened. After the experiment, take the drive belt off the stir, remove the lid, and take the bomb from the bucket. Depressurize it and open it up. And you measure the unburned ignition wire length using a scale on the spool of wire itself, and that's how you determine the energy input. Then you repeat the whole process for the unknown fuel sample. So your expected results, you gotta find the thermal capacitance of the system. We assume the system is 2 kilograms of water and 3 kilograms of stainless steel. You get the CV value of the stainless steel and the CV value of the H2O from the thermo textbook. It's back there. Units are in kilojoules per kilogram Kelvin, and your thermal capacitance is the mass times the specific heat value. We get a value of 9.74 kilojoules per Kelvin. And then define the Q for a known fuel. Q is equal to the delta H, where the delta H is the molar enthalpy of combustion, times the molar mass times the mass used in the application, in this case 1.1 grams, or 1 gram, excuse me. This Q that we found here does not take into account the ignition wire. I did not have the data available to me to produce the value. So this is just the Q of combustion for the benzoic acid. So plug it into our equation, you see the delta T is equal to Q over the thermal capacitance. And we get a delta T of 2.712 Kelvin. The temperature of the water will rise by 2 Kelvin. Assuming the water bath is 25 degrees Celsius, around room temperature, experiment raises the temperature of the water to 300.81 Kelvin, which is 27.7 degrees Celsius. Some possible error sources: you have human error preparing the bomb, not enough, too little fuel, not having a perfect continuity in the ignition circuit, and getting water in the fuel when you add that 1 milliliter into the bomb itself. And your other is instrumentation accuracy. The thermocouple has a plus or minus, like 2 degrees C, so they could be off in that regard as well. Any questions? Or reference the lab manual and the thermo textbook. Any questions?